if I don't show you one example, right? So now I'm going to show you an example. Before I do that, let me again write down the flow chart. I know you know that you need that very much. So the flow chart of conjugate gradient method. So initially, we have x 0 and k equals to 0, and we start just like a steepest descent. So we need to evaluate the gradient at k. Let me see. Gradient at k, right? Let me make this the same format. Okay. Let me make a more clear version of this. Okay, once we have this, we know our x k plus 1 will equals to sk plus some alpha times the dk. Okay, so over here where dk equals to what? Dk will equals to inverse gradient if k equals to 0. Otherwise, it equals to this plus gradient f using the current one dot product x k. Here I use the k minus 1 dot product gradient x k minus 1 times what? The previous d, so d minus 1. Otherwise, okay, if only if k equals to 0, we use the negative gradient. When k is larger, we not only use the negative gradient, we also need to update the direction. And the direction is based on the previous direction. And what's the multiplier in front? It's some value that was derived in the past. So basically, it's gradient k dot gradient k over gradient k minus 1 dot gradient k minus 1. So it's a value over another value. So basically, this is some value. And this will guarantee you your new direction and the previous direction will be Bayesian orthogonal. Okay? So once you do that, you then can do the convergence check. So if yes, converge, your optimal is your latest design. If not, then k equals to k plus 1. And then go back to the first step. And then you move on to the next iteration. So this is basically the procedure of conjugate gradient.
Okay, so okay.
Okay. So if later on in the future when you work on your thesis or write a paper, when you want to utilize optimization procedure, your flowchart could look like this. Well, first, make your drawing nicer. Right? Okay. Now we have the flowchart. Can we try to solve it? Try to solve an example. And let's use a simple one. Remember, if we want to minimize f equals to x1 squared plus 10x2 squared. And let's say my initial gas is, for example, 2. If we do that, steepest descent will do the zigzagging, so it doesn't go to the optimal right away. So let's try to solve it by conjugate gradient. Okay, so initially you treat this as a steepest descent method. So you need to calculate what's the gradient. The gradient look like 2x1 and 20x2. So gradient, let's just directly apply the steepest descent approach. So we have this plus some alpha times gradient f 0. So what we have here is 2 plus 4 alpha 0 and 2 plus 40 alpha 0. Right? We should have this, the gradient for 4 and 20. So we don't know the alpha. How do we determine the alpha? We still need to do the subproblem. So subproblem cannot be avoided. So now we need to move on to the subproblem. Here again, this is the main problem. And here is my subproblem. So for the subproblem, I should have a f alpha, and I plug in 2 plus 4 alpha squared plus 10 over 2 plus 40 alpha squared. So over here, I move on to this subproblem. And this is, I use 1D Newton to solve it with 1D Newton. So for 1D Newton, did I make a mistake?
Maybe alpha is negative, minus alpha gradient.
Negative?
Yeah.
Yeah. I was wrong. Sorry. Okay. Correct. So now my initial gas, let me call this iteration number m. So alpha, let me consider alpha as 1. So m equals to 0. And then so my alpha 1 is alpha 0 minus f prime of alpha 0 over f double prime of alpha 0, right? So this is my 1 over, I need to do a derivative, so I have 2 over 2 minus 4 times 1, chain rule, this time don't forget, plus 22 minus 40, chain rule, no space. Hold on. No. Go back. Okay. So chain rule, I should have negative 40 here. Right? And I should have, sorry. I should have get the forms first. So f prime of alpha is 2 times negative 4 plus 22 minus 40 alpha and negative 40. So maybe I derive this here. That will be negative 16 plus 32 alpha minus plus 32 alpha. Right? Mistake?
No.
Correct, right? So negative 1616 plus 32032 alpha. Yeah. So my f double prime of alpha will be 32032. Did I make a mistake? When someone talking, I feel like I made a mistake. So this will be 1 minus let me calculator 30416 over 32032. So I should have 1 minus 30416 over, so 0.05. Okay. Of course, not yet converge because it is larger than 10 to the negative 3. Not yet converge. So I move on to the next stage. M equals to n plus 1, which is 1. So now my alpha 2 equals to alpha 1 minus f prime of 1 over f double prime of 1. So I should have 0.05 minus, okay. Plus so here I have negative 14.4, and here I have something like this. So the answer should be very similar to what I had earlier. But still the same solution, right? Because this is so small. Am I right? Yeah, should be right. So now this is 0, so converged. And I will update back. So this becomes 2 minus 4 times this. So what is that? So this is 1.8. Oh, this is 0. Really? Okay. Just maybe not a good example. 2 is too close to the solution. Let me use a different number. Because if we move on to 1.8 and 0, the next step you can already converge at using steepest descent. So let me use a different number. Let's start with about supposedly if I move, let's say 5 and 5, about that, then this will take a longer time to converge. So I have 5 and 5, and over here the coefficient is different. Okay, so the entire right hand side is different. The same? Shouldn't be the same. Yeah. Okay. So let me. Okay. So 2. So I should have negative. Okay. So at the end I should have okay. And here is okay. Now when I plug in, what do I have? Maybe I should get more digits. So let me get more digits. Okay, let me take more digits. So Okay. And then minus what? Minus so this is 10.1 over. So of course you should get the same results. Okay, and then when you plug back, okay. So I should have 4.495. So I have negative 0.05. Yeah. Okay. So my previous alpha was I need more digits, otherwise it's not accurate enough. So now we move from 5 to this new point, and let's try to use Stiepy-Stisson again and to see how it doesn't converge. So the convergence check was to check the norm of this. So it's like 4.4495 minus 5, negative 0.05 minus 5. It's like checking the norm of this vector, and the result is calling MATLAB, using MATLAB to calculate. So calculating the norm of negative 0.505 and negative 5.05. So the norm is 5.0752. It's too large, so not converged. So I move on. At the beginning, my k equals to 0, so k now equals to 1, and I move on. If I still use Stiepy-Stisson, here is Stiepy-Stisson. If I still use it, my x2 becomes x1 minus alpha 1 times gradient 1. So this will give me, this is like doing your homework. So 4.495 negative 0.05 minus so 8.99 alpha 1, and then plus 1, because 0.05 times 20, not yeah, 20, that's 1, so alpha 1 here. Okay, so now you need to go to a subproblem So let me do some copy. Oh no. Oh no. Okay. So previously I had this. So now I move on to my subproblem. But over here, many things is different. Move to a subproblem. So oh, 10 times. Okay, so here my gradient is different. Okay, so if I get them, I'm relying on MATLAB. 4.495 minus 8.99 times alpha times negative 8.99 plus 20 times negative 0.05 plus alpha. That would be simplify. Oh, evaluate. No. What's the value of this? Okay, so 81.82 and what? Oh, sorry. So 1A1.64 alpha and minus 81.82. So the gradient, the second order of gradient is 1A1.64. So if I plug in, I should have 1A1.64 minus 81.82. I should have 99.82, and here I have 1A1.64. So at the end I have what? 99.82 over 1A1.64. So my alpha is different. So like I show you, alpha shouldn't be the same. Okay, so do it again. Plug in here, 0.4505 minus 1A1.64, And when you plug in the equation 181.64 multiply 0.4505 minus 81.82, you have a very small number. So of course, you have a same value of alpha. So now you can plug back because converged. So when you plug back, you will have times 0.4505 plus 0.4505, and what would you have? This is 0.445 and this is 0.4005. So you are moving gradually toward 0, 0, but not yet 0, 0. So this probably will take several more iterations until it converges, right? So more iterations for steepest descent. But if we actually use conjugate gradient for the second iteration, what will happen? So we stop of the steepest descent here.